Welcome back class to our course Mechanical Behavior of Materials. So we have already discussed about two strengthening mechanisms, precipitation strengthening and dispersion strengthening, and the second one solid solution strengthening. Today we are going to discuss about grain boundary strengthening. Okay. So here I have shown an optical micrograph of a polycrystalline alloy. Okay, so you can clearly see here grain boundaries. So these are your grain boundaries. Okay. Now, why do we see grain boundary between two grains? So here I have shown on the right side schematic where you have grain 1 on the left side and grain 2 on the right side. And what you can see here is a change in the orientation, right? So orientation changes from drain 1 to drain 2. And you have a drain boundary here. So this is your drain boundary. Okay, so what you see, you have an orientation here, something like this, right? This is your orientation, but here it is in this direction. It changes. So there is an angle here, right? So the orientation between the two drains, it is changing, and that's why we are going to see a boundary between the two drains, and that boundary is called drain boundary. Now this drain boundary is also contributing towards the strengthening of a given alloy system, and we are going to learn about this particular concept, why drain boundary is contributing towards the strengthening, what makes it suitable to increase the strength of a given alloy system. Okay, so here I have shown dislocation, and then you can also see two drains. So we have drain 1, then drain 2, slip plane, drain boundary. So we have a dislocation because dislocation movement needs to be restricted so that we can increase the strength of the alloy, and that is the crux of all strengthening mechanisms. We have discussed that before. Okay, so what is happening now, that suppose this dislocation is moving on the slip plane and reaches to drain boundary, right? So what it says, it has to change the path now, isn't it? Because the orientation has completely changed from drain A1 to drain 2, right? That is point number 1. And second, the drain boundary itself has an atomic disorder, right? So there is a discontinuity of the slip plane also from one drain to another, and this leads to the strengthening of the alloy because of the change in orientation between the two drains. So strengthening occurs due to point number 1, a dislocation passing into drain 2 from drain 1, will have to change its direction of motion. Okay, why? Because there is a crystallographic misorientation. So due to crystallographic misorientation. Okay, that is point number one. And point number two is the atomic disorder within a grain boundary region will result in a discontinuity of slip plane from one grain to another. Discontinuity of slip plane from one grain to another. That means grain 1 to grain 2. So when a dislocation moves and it reaches towards the grain boundary, right, it sees that the slip plane direction has changed. So it was like this, now it is like this. Okay, so the slip plane direction has changed. That is number one, and it has to also change the direction of motion, isn't it? So these two factors leads to the strengthening in the alloy, and this is happening because there is a change in orientation of the alloy. Okay, now what will happen when a dislocation is near the grain boundary and it is not able to change its position, right? Change the slip plane. It is not able to traverse through the grain boundary. It is going to pile up at the grain boundary. So let's discuss about what is called pile up. So pile up of dislocations. Okay, so if dislocations are not able to traverse through obstacles such as a grain boundary, in this case, what will happen? It will lead to piling up. Pile up of dislocations at GBs. So grain boundaries, right? So what is happening? A dislocation is coming. So let me draw a grain boundary here. So suppose you have a grain boundary. So this is your grain boundary. So I will write GB for grain boundary. Becomes easier. Okay. So you have a GB here and then a slip plane. A dislocation is moving on a slip plane and it reaches towards to the grain boundary. It reaches at the grain boundary. Now it is not able to traverse through the grain boundary. So it cannot cross. So it will be staying there, right? Now suppose, so this is say dislocation number 1. Now this is dislocation number 2. A second dislocation is now moving, right, on the same slip plane, and then it also reaches towards the grain boundary, right? But what will happen? The first dislocation is going to repel the second dislocation. And mind it, this is happening when there is a applied stress, right? So you have a applied stress, and that's why dislocation is moving, right? So first dislocation is already at the drain boundary. Now second dislocation is moving along this direction. As soon as it reaches towards the first dislocation, the first dislocation is going to repel the second dislocation, right? And second dislocation now will be at equilibrium due to the applied stress and the stress due to dislocation number 1. So they are going to maintain a certain distance here. Okay, now let's see what happens when we have third dislocation. So again, the same drain boundary, slip plane. So we already have dislocation number 1, then dislocation number 2. Now a third dislocation is coming. So we have dislocation number 3, and somewhere here you have source of dislocation, which is ejecting dislocations continuously on this slip plane, and because of the applied stress here, dislocations are moving on the slip plane. Okay, so the third dislocation is moving along this direction. Now what will happen, as soon as it reaches to say this position nearby dislocation 1 and 2, the third dislocation sees a stress field because of the applied stress, and the one and second dislocations, they are going to repel the third dislocation. So again, third dislocation will be at equilibrium position because of the applied stress and the repelling stress of 1 and 2. Okay, so what will happen, the third dislocation will come, and then it will also occupy a position something like this. So what you are saying, that the distance between first and second dislocation is lower than the distance between second and third dislocation. Now the fourth dislocation will come, and it will also be somewhere like this. Okay, so now this distance, if I mark this as say x1, this is say s2, say s2 3 and x1 2, and this is s3 4. So you can clearly see that s3 4 is greater than s2 3, then greater than x1 2. Okay, so as you move away from the drain boundary, the distance between the dislocation increases, and this is happening. Why? Remember, whenever dislocation 2 comes, it sees the repulsion only from dislocation number 1. Okay, so there will be some distance. Now when the third dislocation comes, it will see a repulsion because of a combination of 1 and 2. So it will have slightly higher repulsion stress compared to what was observed by dislocation number 2. Okay, so it is going to maintain a slightly higher distance. Now when dislocation 4 comes, you are going to see this dislocation going to see the repulsion stress because of a combination of 1, 2 and 3. So there will be another larger distance between dislocation number 3 and dislocation number 4. So what you see, that these dislocations are actually piling up in front of the drain boundary. Okay, and that's why we call this phenomena as piling up of dislocation at an obstacle. In this case, the obstacle is drain boundary. Okay, so we can write that dislocations piled up against the obstacle, and in this case it is drain boundaries, they are going to produce a back stress. So when the dislocation 2 comes, dislocation 1, which is already there in the pileup, it is going to produce a back stress on dislocation 2. Okay, similarly when dislocation 3 comes, both dislocation 1 and 2, they are going to produce combined back stress on dislocation number 3, and this back stress is actually, it is opposing the dislocation motion. So all the pileup dislocation, they are going to produce back stress to oppose the motion of any additional dislocation. Okay, that is point number 1. Point number 2 is dislocation will be tightly packed together near head or near drain boundary. And as you move away from the drain boundary, they will be widely spaced. As one moves away from the drain boundary, the distance between dislocations increases. Okay, that means they are widely spaced. Widely spaced, right? And this is happening towards the source. Okay, so you can clearly see here, if I talk about these 4 dislocations here, okay, so near the dislocation, near the drain boundary, you can see dislocation 1 and 2, they are tightly spaced, and as you move away from the drain boundary, you can see that the dislocations are widely spaced, and your source is here. Okay, so there will be n number of dislocations, right? It's not only 1, 2, 3, 4. There will be lots of dislocations which are going to be piled up at the obstacle. This obstacle in this case is drain boundary, and mind it, the dislocations are moving because we have already applied a stress. So there is a application of stress also, and because of that, dislocation is moving on the slip plane. Okay. Now, let me again draw this pileup. So this is your GB. So I will give you one formula now. So this is a slip plane, and then we have lots of dislocations, and we have to now maintain the distance also. So something like this. Okay, so it is increasing as you move away from the drain boundary, and somewhere here you are going to have nth dislocation. This is 0, 1, 2, 3, 4. So n number of dislocations, they are getting piled up at the drain boundary, and the applied stress is tau. Okay, and the distance I am measuring from the drain boundary, and I will tell you what is I here. Okay, so you have all these edge dislocations, they are on the same slip plane, right? So the general formula for edge dislocation, the force between two edge dislocation, we can write as GB square by 2 pi 1 minus mu x square minus y square divided by s square plus y square whole square. Okay, so y is 0 here because we are talking about the same slip plane, and two dislocations, those who are interacting, they are on the same slip plane. So y becomes 0. So force in this case we can write as GB square by 2 pi 1 minus mu s cube by s4, or finally GB square by 2 pi 1 minus mu into 1 by x. So in this particular pileup case, it depends, the force between two dislocation depends upon the x value, right? Distance between these two dislocations. Okay. So now I have already mentioned that each dislocation in this pileup as shown above is under equilibrium. Okay. So if I consider dislocation number 3, it is under equilibrium because of what? Because of the applied stress and then interaction between all the dislocations in the pileup. So if I talk about say dislocation number 3 here, if I just choose this one, so you have, so this is dislocation number 3. So you have applied stress tau. Then you have again stresses because of the dislocations which are present on the slip plane on the left side of the dislocation, that will have the same direction as the applied stress. Then there will be repulsion from 0, 1 and 2 dislocation, that will be on the opposite side. Okay, so dislocation number 3 is under equilibrium because of two effect of applied stress okay, and then stresses due to the other dislocation in the pileup. Okay, so now let's assume that this all dislocations are of S character and the parallel. So if I want to understand the force on a particular dislocation, so the resulting force acting on the ith dislocation, we can obtain, or we can, since this is in equilibrium, right? So we can write this as tau b minus sigma j equal to 0 to j equal to n, I is not equal to j, and then gb square divided by 2 pi 1 minus mu, and then x. So xi minus sj, and since this is in equilibrium, it will be 0. Okay, so a particular dislocation, if you see, I was talking about number 3 here, right? So this particular dislocation number 3, this is under stresses of applied stress and then the stresses due to the other dislocation, and this is under equilibrium, dislocation number 3, right? So the forces on dislocation number 3 should be 0. Okay, so now because of the applied stress, the force on the dislocation will be given by tau b. Okay, and the interaction forces between this dislocation number 3 and other dislocations will be given by this summation. Now the combination of these two should lead to 0 because dislocation number 3 is under equilibrium. Okay, and you can calculate this. Okay, so if you say consider, let's see, I have a dislocation GB here, and say we are just considering dislocation 1 and dislocation 2. Okay, only one dislocation in the pileup. So here it will be now 0 and 1. Okay, so it will start with 1. So 0 and 1. Okay, so now if I want to calculate what is the force on first dislocation, so tau b, so I can write this equation. This equation will become tau b minus summation है Okay, so j equal to 0 and I is not equal to j. So I here is 1 because we are talking about the ith dislocation, and here I is equal to 1, the first dislocation. So this will be gb square divided by 2 pi 1 minus mu xi, that means x1 minus j equal to 0 to n is equal to 1 here, so it can go to maximum 1. So x1 minus s0, and second term will be 0, s1 minus s1, that will be 0 anyway. So we that cannot be counted, I is not equal to j. Okay, so this is the equation for ith dislocation. Similarly, you can calculate for dislocation number 2. So, or say you have now added another dislocation, dislocation number 2, and now you want to calculate what is the force on dislocation number 1. You can use the same equation. So you are going to have tau b because of the applied stress. Then you are going to have a repulsion force from dislocation number 0. So if I have number 1 here, then number 2 and number 0 here. Okay, so on number 1, if I want to calculate, so you are going to have tau b in this direction because of the applied stress. Now because of the dislocation 2, you are going to have another force from dislocation number 2, and then from 0 you are going to have force in this direction, and summation of all this should be 0 because 1 is in equilibrium. And if you do that, if you use this particular equation on the top, you can solve this equation very nicely. Okay, and remember n is the number of dislocation in the pileup. So this is the generalized equation, this one, for resulting force on a ith dislocation if you have n number of dislocations in the pileup. Okay, now at the leading dislocation, the first dislocation in the grain boundary here, so I'm talking about this particular dislocation. Okay, so what are the forces there now? You have forces from the dislocations in the pileup. So you have lots of dislocation here, nth number of dislocation, right? And then you are also applying tau. So on the leading dislocation in this region, you have a combination of stresses because of the applied stress as well as repulsive stresses from all the dislocations which are in the pileup. Okay, now what will happen? This will lead to a very high stress concentration in this region at the leading dislocation, isn't it? Okay, so the leading dislocation in the pileup, okay, it will have stresses due to other dislocations in the pileup and also applied stress, right? Stress due to applied stress, and all of them are acting on the same direction, right? Okay, so what will happen? This will lead to a very high stress concentration. Okay, so this will lead to high stress concentration at the region of leading dislocations. Okay, so now what can happen if you have a very high stress concentration? Two things can happen. One, the yielding can happen on the other side of the dislocation. That means you can generate new dislocations on the other side of the dislocation, and that other side of the drain, and that drain can yield. That is point number 1. So if you have drains here, and say you have piled up of dislocations, and at the leading dislocation here you have a high stress concentration. Okay, so what can happen, this particular drain that has not yielded yet, because of the high stress concentration in the leading dislocation here, dislocation source such as Franklin source can activate in the drain 2, if I name as drain 2 and drain 1 here. So yielding can occur in drain number 2. You can have nucleation of dislocations. That is point number 1. And second, instead of the yielding of the second drain, you can initiate cracks at the drain boundary here at this point. Okay, so you can nucleate the crack. So these two things can happen if you have a high stress concentration at the leading dislocations because of the combination of applied stress as well as stresses due to other dislocations in the pileup. Okay, so this will lead to 2 points. Point 1, yielding can occur on the other side of the drain boundary, or say in this schematic here, drain 2. Okay, so you are going to see nucleation of dislocations. That is point number 1. And second, you can see nucleation of crack at the drain boundary. Okay, and again this is happening because you have high stress concentration at the leading dislocation because of the pileup of dislocations at the drain boundary. Okay, now what is the value of that high stress concentration we are talking about? And that value was calculated approximately to be tau b and tau b, sorry, tau a, where n is your number of dislocations in the pileup. Okay, and tau a is your applied resolved shear stress. Okay, so the tau what I was mentioning before, now it is tau a, and that is what, that is resolved shear stress on a particular slip plane. Okay, so if you have a drain boundary and then you have lots of pileup of dislocations, so the stress concentration or the stress value, which is tau star here, at the leading dislocations because of the applied stress and dislocations in the pileup can be given by n multiplied by the applied resolved shear stress. So what is happening? It is actually multiplying with the number of dislocations in the pileup with the applied resolved shear stress. Okay, so this derivation was introduced by Okay, and so tau star, this is stress at the leading dislocation. Okay, due to presence of other dislocations plus applied stress, both. And that's how you are getting the stress concentration. So overall, what you are seeing, the effect of n dislocations at the pileup is to create a stress which is n times greater than the applied stress, isn't it? So overall, you can say the effect of n dislocations in the pileup is to create a stress at the leading dislocation which is n times greater than the tau A, and which tau A is applied stress, applied resolved shear stress, because we are talking about the slip plane, on the slip plane, shear stress. Okay, so if you have n number of dislocations, you are going to increase the stress at the leading dislocation, which will be n times applied resolved shear stress. Okay, now you have to also realize that all these dislocations which are piled up at the grain boundary, they are also going to apply back stress at the source. So if you have again GB here and lots of dislocations, and suppose you have a source here, say a Frankfurt source, which are generating dislocations continuously. Okay, so all these dislocations in the pileup here, right, they are going to apply back stress on the Frankfurt sources itself, right? So this doesn't mean that Frankfurt source can generate dislocation continuously. There will be certain number of dislocations this can generate because of the back stress from the dislocations in the pileup. Okay, so how many dislocations you can have in the pileup? There is a restriction, and that number is given as n equal to L pi tau A by alpha GB. Okay, and where tau A is resolved shear stress. Okay, alpha is geometrical constant, and it is given as 1 for screw dislocations or 1 minus mu for edge dislocation. B is your Burgers vector, okay, and L is the length of the pileup. Okay, L is length of the pileup. That means, say if the pileup is only up to this point, so we will call it as length. Typically, it will be from the source. Okay, So due to back stress, you can generate only certain number of dislocations. Let me write down that also. Due to back stress from the piled up dislocations, only certain number of dislocations generation. Okay, and that is given by n, and n is given by this equation here. Okay, so now you know the number of dislocations which can be piled up when you have applied stress of tau a, and length of the pileup is given by L. So I can write what is the length of pileup from this particular equation on the top. That will be given as alpha n GB by pi tau a. So this is the length of the pileup. Okay. Now suppose the dislocation source is at the center of the drain. So you have this drain, and here is your Frank source. Okay. So length of the pileup of dislocation. So this is your pileup of dislocation. So this length L in this case can be given as d by 2, where d is your drain size. Okay, so we are assuming that the source which is generating the dislocations on that particular slip plane, which is leading to finally the pileup of dislocation, that source is sitting at the center of the drain. Okay, so the pileup length L will be given as d by 2, where d is your drain size. So I can write this as d by 2 equal to alpha n GB by pi tau a. This is another equation. Okay, and assumption here is that the Frank source, okay, or the source which is generating dislocation is sitting at the center. Okay, so now suppose you have reached to drain boundary here. So you have reached to drain boundary dislocations, and now you want this dislocation to just traverse through the drain boundary. So that will also require some amount of stress, isn't it? If you want to traverse these dislocations, not drain boundary, if you want to traverse these dislocations through the drain boundary, you require some critical stress value to overcome that particular barrier. So if I assume that tau c is that critical stress which is required to overcome this particular barrier, right, we can write an equation. So if tau c is the critical stress required to overcome the GB, okay, obstacle. So in this case, obstacle is GB, okay. And this overcome GB obstacle, that means dislocations in the pileup are able to traverse through the drain boundary. Okay? So dislocations in the pileup are able to traverse through drain boundaries. Okay, then I can say that if I consider the leading dislocation, what was the stress at the leading dislocation? N tau a. Okay, so N tau a has to be greater than equal to tau c. So if the stress at the leading dislocation is higher than the critical stress required to overcome the drain boundary, for these dislocations can actually burst from the drain boundary, through the drain boundary, and that relationship will be given by this particular equation. It has to be minimum tau c, so it is greater than equal to tau c. Okay, now n we know, we use this formula on the top, so n we can write as d pi tau a divided by 2 alpha gb, that is n from this particular equation we are using, and then tau a is already there, equal greater than equal to tau c. Okay, and then we can write tau a square is greater than equal to root over 2 alpha gb tau c divided by pi, and d I am taking out, it will become d to the power minus half. The square will not be there, okay, because I have already taken square root on the right hand side. So if I want to move dislocations through the drain boundary, the applied stress should be this much. Okay, it is a function of diameter of the drain size, and again remember we are assuming that the Franklin source is at the center of the drain. Okay, so we can overall write this as tau a greater than equal to tau naught plus k d to the power minus half, where k is this particular constant. So this is your k. Okay, and we have added tau naught because of the friction stress in the lattice. That also needs to be overcome, right? Even if you don't have drain boundaries, the friction stress, which is pile stress, that has to be overcome if you want to move the dislocation. Okay? So tau naught is added to take into account the friction stress needed to move our dislocation. Okay, so overall you are getting this particular equation, and you know, you will see eventually that Hall-Petch relation is also given by this equation, almost this equation, where we are replacing tau with sigma. Okay, so Hall-Petch theory. So whenever we talk about drain boundary strengthening, this particular theory will be always discussed about. Okay, so what is Hall-Petch equation, etc., etc. It gives a very nice description or nice relationship between the strength and the drain size. Okay, and remember the drain size is related to drain boundary. Okay, so in a given volume, if you have larger drain size, the drain boundary density will be smaller. Okay, so Hall and Petch, both are scientists. They postulated that dislocations can burst through drain boundary. That is what we have discussed in the previous session also. Okay, and to do that you require large number of dislocations in the pileup, so that you have large stress concentration which can overcome tau c, which is a critical stress required, right? So valid for large number of dislocations in a pileup. Okay, and we know tau a is greater than equal to tau naught plus K d to the power minus half. So this is the genesis of Hall-Petch relation, and this is what Hall-Petch actually postulated. Later on, what happened? Cottrell came and he proposed another theory. So what was the proposition here? So, he mentioned that it is virtually impossible for dislocations to burst through the boundaries. Okay. Instead, what will happen, since you have a stress concentration at the leading dislocation in the pileup, they are going to activate dislocation sources in the adjacent drain, such as Frank-Ritz source. Okay, so that is what they proposed, and they also gave a formula for that. So it is virtually impossible for dislocations to burst through drain boundaries. So instead of bursting of dislocation, you will have yielding of dislocations, yielding of drains, neighboring drains, because of the nucleation of dislocations, or say activation of Frank-Ritz source in the neighboring drain. So the stress concentration produced by pileup in one drain activates dislocation source in the adjacent drain. Okay, so if you have, say, a drain and you have Frank-Ritz source here, FR source, you then have pileup of dislocations, something like this. Okay, so in the neighboring drain, okay, so somewhere here, say, you are activating Frank-Ritz source. So if it is drain number 1, this is drain number 2. Because of the stress concentration in the leading dislocation, you are activating a Frank-Ritz source in the neighboring drain, say at a distance of R from the drain boundary. So this particular distance here is, say, R. Okay. So the stress to activate the Frank-Ritz source in the neighboring drain this was given by Cottrell. Okay, tau A should be greater than equal to tau naught plus 2 tau C R to the power half d to the power minus half. So almost similar to what we just saw. Instead, you have this term here, but it is also related to diameter of the drain. Okay, so whether it is Cottrell theory or Hall-Petch theory, we just learned both are related to diameter of the drains, and it says that increasing the drain size will require lower amount of stress for the plastic deformation. Okay, that means if you want to increase the strength of the alloy, you have to reduce the grain size, and that is what Hall-Petch relations discuss. Hall-Petch Hall-Petch relation. So what is this relationship? Yield strength follows Hall-Petch relation for almost, most of the materials. And this relationship is given as sigma y equal to sigma naught plus k divided by root d. Okay, where sigma y is your yield strength of polycrystalline sample. Sigma naught is your frictional stress for dislocation movement. Frictional stress for dislocation movement, and D, we have discussed this is drain size. Okay, so what it predicts, if you reduce the drain size, sigma y is going to increase, right? And that is the drain boundary strengthening concept. So if you want to increase a strength of a given alloy system where you say you cannot change the alloying elements, so solid solution strengthening you cannot modify, and suppose that particular alloy system is also not able to give you precipitate, so precipitation strengthening is out of question. So one of the ways to increase the strength of that particular alloy system is to use drain boundary strengthening concept, where if you reduce the drain size, then you are going to increase the strength of the material, and that is what Hall-Petch relation is all about. Okay, so decreasing the drain size will lead to increasing sigma y. So the more you decrease the grain size, there will be increment in sigma y. Okay, but this is not valid in nanometer range. That is called inverse Hall-Petch relation, but we will not go into that in this particular course. So if I plot, say, sigma y versus root d, suppose you take an alloy and you varied the grain size in that particular, so you took different sample, you did some heat treatment, and you are varying the grain size. So you, in one sample you got D1, in another sample you got D2, and so on, and then you also did tensile test and you figure out what is the yield point, okay, or sigma y here. So you can nicely plot something like this, okay, where slope is going to be, so this is 1 by root d, or say d to the power minus half. So slope is going to be k, and this is going to be sigma naught. Okay, so it's y equal to ms plus c. So h here is d to the power minus half. So m, or slope here, it's k, which is a constant, and then c here, the intercept here is sigma naught. So this is what Hall-Petch relation is all about. Okay, and remember, Hall-Petch relation is not a universal law. It is valid for a certain grain size range. If you go to a nanometer size range, very, very small grains, then this relationship is not going to be valid. But in most of the engineering alloys, we are talking about micron meter size of range. So we typically tend to use Hall-Petch relationship for most of the engineering materials. Okay. So in this lecture, we have discussed the details about drain size strengthening or drain boundary strengthening. So we have till now completed 3 types of strengthening mechanisms for precipitation strengthening or dispersion strengthening, then solid solution strengthening, and grain size strengthening. So in the next session, we will discuss about strain hardening, okay, or word hardening. You have some little idea about it when Professor Shashank Sekhar discussed with you about the tensile curve, okay, but we will discuss about this particular concept in more detail in the next lecture. Thank you.